Hello, my name is Amy, and I worked with Teen, Grace, and Jimmy. For our final project, we created a low-latency financial compute accelerator for options pricing and market feeds. High-frequency trading, or HFT, is the real-time processing of market data and evaluation of pricing modules. Due to the nature of the field, any small improvement in latency can translate to significant financial advantage. In this project, our goal was to accelerate spot price calculation and options pricing using HLS to implement it on an FPGA and validate the design using real NASDAQ itch market data. On the right, you can see our overall system data flow. We have three main modules for the project: the itch parser, which takes in the NASDAQ exchange market feed and parses it into the different fields, the order book that maintains all the orders and calculates the spot price, and the Black-Scholes engine, which uses the spot price to then compute the options pricing. Options pricing is important in the field of trading as it can be used to make more informed decisions for investors. Overall, our goal is to improve efficiency for this computation-intensive trading application by offloading the entire pipeline onto hardware using HLS. As mentioned previously, the itch parser takes in raw NASDAQ total itch binary data and decodes it into different fields. For our project, we took one-day market data and only took the first 500 messages of the 6 desired order types to feed into the module. The specific order types we looked at were add order, order executed with price, order cancel, order delete, and order replace. All the message types and their fields can be seen in the diagram on the slide. The itch parser would first identify the message type from the message header. Because each itch message type encodes different fields at different bit positions, the parser must slice the binary message accordingly. After the message is decoded, the parser outputs a stream of decoded order messages to the order book.
So, following the parser, you have the order book, which is effectively the system's memory. Unlike the other modules that might process data in isolation, the order book is responsible for maintaining the persistent state of the entire market. Functionally, we take the decoded stream of messages, which may contain adds, cancels, executes, or replaces, and organize them into two sides of the market. You have the asks, which are the sellers, where we look for the lowest price someone is willing to sell for, which we call the best ask, and the bids, which are the buyers, where we look for the highest price someone is willing to pay for, or the best bid. Our main goal here is to calculate the spot price. After every single message that comes in, we update our records and calculate the average of the best bid and best ask. It's important to note that this spot price is basically critical input that gets passed downstream to the Black-Scholes engine to actually price the options. And to implement this on the FPGA, we had to be very specific about our data structures. We maintain two primary arrays to store this state: bid orders and ask orders. We allocated these arrays to hold max orders, which is defined as 4,096 entries each. We chose this specific size as a design trade-off. It's large enough to capture the depth of the market data we are simulating, but also small enough to fit within the resource utilization for our FPGA. I'll now describe the logic of the workflow. The logic flow basically for the module is iterative. You have the update, which is when a message arrives, we immediately add, remove, or update the order in the respective array. Following that, we have the scans, where we iterate through the active orders in this array to identify the new highest bid and lowest ask. And then compute, which is where we take the average of those two values to generate the spot price. We then feed the spot price into the Black-Scholes engine for computation. I'll now let Grace explain the Black-Scholes.
The last module runs the Black-Scholes-Merton algorithm, which is a mathematical model used to determine the fair price of a European-style options contract. It calculates call input option pricing, where the call option gives you the price you pay for the right to buy the underlying asset at the strike price, and the put option gives the price you pay for the right to sell the underlying asset at the strike price. The formulas include variables for spot price, strike price, risk-free interest rate, volatility, and time to expiry, where the spot price is taken from the order book and the remaining variables are fixed for our purposes. Now let's move on to the optimizations. The itch parser does not have many optimizations because its core function is to read specific fields of a given binary message. The itch protocol uses big endian notation for all integer fields, and the helper functions to read these fields have been inlined and unrolled. Inlining removes the function call overhead and allows for optimizations across function boundaries, and loop unrolling duplicates the hardware to reduce latency.
A lot of the optimizations to our order book actually came at a software level, especially in respect to what data structures we chose to use. Before we go over the later iterations, I want to talk a little bit more about the first iteration and the problems that came along with it. So recall the goal of the order book. we want to keep track of the highest and lowest prices, and we want to query this fast. So one way we can do this is, well, we could use heaps to implement this. And by using heaps, we can prioritize based off the price. And then each time we want to query, we just query the top node and we get the highest price that we want. But there are problems with this, because with the itch protocol, whenever we get a message to cancel an order, that message contains only the order ID and not the price. So we might have an internal heap with these 3 orders, and the top order has price 7, but we might get a message asking us to delete order ID 2. But the problem is, well, we start at the top of the heap, and where is ID 2? We don't really know how, there's no guarantee of where to find this unless we search the entire tree, which isn't really ideal. One way we can get around this is by using hash tables. So how this might look is, well, maybe we might have these 3 add orders, and for now, in the very beginning, we have no priority queue, no hash table, right? So let's say we process the first order. Well, since there's nothing, we just initialize the heap, and this is at the very top. And then for the hash table, we create a binding from reference IDs to the number of shares. So here we map ID 0 to 4 shares. And then we do a similar thing for the second order. In this case, since this has a higher price than what's in the heap, this becomes a new top node. And we also create a binding in the table for ID 1 and 2 shares. And then we do a similar thing with the third add order. But in this case, since it has lower price, it doesn't become the top node. And similarly, we create a binding from 2 to 8 shares. So now that we added a couple of things, right, we might get a set of remove messages. So for example, we might get these 2 messages here, and the first message is asking us to remove order ID 2. And like before, this is in the middle of the table. But now with this hash table, we just ignore the heap. So we go to the table and we're like, okay, well, ID 2 has 8 shares. We want to remove 8. Now it has 0. All right, but we still don't know where it is in the heap. Or even though we can see it here, like we don't know. And then now we just process the second order and we just forget about the first one. And then we do the same thing. We skip the heap and we just go to the hash table and we go to ID 1, remove 2 shares, and this becomes 0. All right, but this is different because, well, we modified the top node. And we can check the top node fairly quickly and see, like, okay, well, we can cross-reference this with the hash table and see that, okay, the top node has no shares. We can remove this in this case. So then we can remove this top node and then we can do rebalancing. And after rebalancing, we find out, okay, well, we have this new node. And then now instead, we can also want to check this node to make sure that it has shares. And in this case, we look at this and we're like, okay, well, this actually doesn't have shares either because we actually removed it before, but it hasn't reflected in the heap. And then now we update the heap to reflect it, and then boom. Now we have a single node left. This has shares, so we don't really remove it. That's kind of how that worked. And but the problem with this implementation, well, it did suck. And it sucked for a couple of reasons. One thing is the hash table in like bad situations can end up leading to a bunch of scanning of the table. Yeah, we might just end up probing a lot, and it just generates a long linear scan. And this kind of thing isn't very parallel. And the priority queue rebalancing wasn't parallel either, even if the runtime complexity was low. So instead of going on with this iteration, we tried something else. So scratch this, and the next iteration we tried something simpler, just arrays.
For the Black-Scholes module, we had 2 main optimizations. In our original implementation, we had a custom log and exponential function that we optimized using the inline and unroll pragmas. However, we then reverted back to using the standard log and standard exponential functions as we found that they were a lower latency. Secondly, we used the inline pragma to save resources from function call overheads. These tables show the results from our design. We compared our optimized design to 2 baselines, one where the order book was implemented with a hash table but couldn't be routed and ran on a Z-board due to its complexity, and one where the order book was simplified to using arrays and able to be ran on the Z-board. For ECE Linux, it can be seen that the optimized design was able to achieve a speedup of 93,332 times compared to the baseline hash table order book, and a speedup of 5.308 times compared to the baseline array order book. For the hardware implementations, the optimized design was able to achieve a speedup of 1.152 times for software software and 2.958 times for hardware. These optimizations came with a trade-off of higher resource utilization, in which the optimized design had a 1.577 times increase in area.
Now onto a quick demo. First, I'm going to comment in these 3 sections to show the functionality of our system. Due to synthesizability and timing, we've removed the print statements when running Vivado HLS and generating the bit stream. But for now, I'm going to run HFT CSIM to see how our whole system works. And as you can see here, for each message, there is the type and price provided in the message. This information is fed to the order book, which outputs the spot price. The spot price is chosen by the best bid, which is the highest price that any buyer is willing to pay, and the best ask, which is the lowest price that any seller is willing to accept. And that's why there may not always be changes in the spot price. But from here, the spot price is fed into the Black-Scholes engine, which outputs the call input prices. And finally, here in the summary section, you could see we input the first 500 messages from this sample market day, and a majority of the messages are ad orders. And during the design process, we also had other input files with 2 messages per type to ensure functionality of all message types. But we wanted a demo here with a more representative dataset. Moving on to the FPGA, I've already uploaded the bitstream and navigated to the Zboard directory. So after running make FPGA, we get a total runtime of 33.602 milliseconds.